Welcome. For lab number 6, it's a two-part lab. The first part has to do with advection. So if you go to this particular link here under the June 16th through 22nd, you will actually, I have a video that shows you how to identify significant advection, because recall advection is made up of 2 questions in your forecasting exercise. And so it's probably a pretty good idea for you to understand what advection is. Right now, I'm working on part 2 video, which is instability and advection. So I've actually already written the lab as I'm recording this part 2 video. I've just got to upload it, but I need to finish this part here. So let's spend a few minutes and talk about instability. Recall that there are 2 things that we need to produce clouds and precipitation. One is moist air, which we'll cover in Chapter 4 here shortly. And we talked about how to identify sufficient moisture. And in fact, just kind of as a reminder here, if you go to the 850 millibar map, we look for dew point depressions. Recall that's temperature minus dew point. Now keep in mind, since we're at 850 millibars, that's approximately a mile up in the atmosphere. The height of that surface varies based upon temperatures in the atmosphere. But you'll see in Omaha, the dew point depression here is 10. There's a 10-degree spread between the temperature of 12 Celsius and a dew point temperature of 2 Celsius, about a mile up in the atmosphere. There's a dew point depression of 10 there. Dew point depression of 8 over in Davenport, Iowa. Recall that we define sufficiently moist atmosphere at 850 millibars with a dew point depression less than or equal to 5. We do have some moisture up here in Minnesota, and you'll see right here there's a 3 dew point depression in northern Minnesota. Down in Minneapolis, a 3 dew point depression. So let's get back here for a moment. What to look for in terms of what we would consider an atmosphere that is unstable. So 2 things that we need. We need to know for clouds and precipitiform, is there sufficient moisture? And you would look at this map here. And is there a way to lift that moist air to a level in the atmosphere to which it condenses and actually forms a cloud and eventually precipitation? Now, in the lab that you're doing, if we go down here at the time of this video, lab number 5, mountain simulation, you're learning why it is important to lift moist air up to a certain level in the atmosphere, to lift it vertically, to where it eventually forms a cloud and produces precipitation. So you're working on that as I'm putting together this particular video. Well, when we look at instability, an unstable air mass, that means air will rise on its own. And we'll get into that next week, where we'll start talking about stability and cloud development. So I have a PowerPoint here and a few lectures. But for the lab that you're going to be working on for this particular week is a 2-part lab. One part of lab number 6 is on advection, the other is on instability. For instability, we're going to look at 2 levels in the atmosphere. Again, when we're talking about an unstable atmosphere, we're talking about air, and if it's sufficiently moist, moist air will rise on its own. Or a cold front can actually lift moist air up. That's why we look for precipitation and cloud cover near fronts. You'll notice, for instance, if you go up to a surface map, if I click on this surface map, you'll notice that typically precipitation is associated near fronts. That's because a front is acting kind of like a plow. It lifts the air. So for this particular lab that you're going to do, you're going to look at 2 different levels. You're going to look at the 850 millibar level and the 500 millibar level. We're going to look for a temperature difference of 25 degrees Celsius between the 850 millibar level, which is about a mile up, and the 500 millibar level, which is approximately, let's see, about 3.3 miles on average. Again, that changes depending upon the temperature of the atmosphere. So we're looking for basically temperature decreasing with height, and we'll understand why that's important for stability when we get to this particular week here and we're dealing with stability and cloud cover. So let me just take a look at 850 millibars. Now we look at this to look for moisture, but we're also going to look at temperature at 850 millibars, because according to the forecasting program that we're using, you'll recall question number 13. Let me go up to forecasting here. If I go to question number 13, and we're talking about an unstable atmosphere will allow air to rise. And so if I click on this link, I can see that for this program, you need at least a 25-degree change in temperature to produce rising air. In other words, the 500 millibar needs to be at least 25 degrees cooler than the 850 millibar surface. So that's why it's important to figure out temperatures at 850 and 500. And one of the ways that you can do this, you can click on this particular map, and you see that today, this particular analysis was done for 12Z, which would be 7 a.m. this morning, and for June 12th, 2012. And we see that winds in our area, because we're forecasting for Des Moines here, are out of the northwest. And so if our winds are coming from out of the northwest, maybe I want to look back toward the northwest to see what type of temperatures are approaching. And I see the average temperature at 800, or the average wind speed at 850 millibars. I have a 35 knot wind here in Davenport, 20 knot in Omaha. It looks like we got 25 in Minneapolis. If I take the average of these three, 25, 20, and 35 would be 80 divided by the three stations. So we're looking roughly at about 26 and a half knots from the northwest. Let's make the math easy. Let's just say the average is 25 knots. So if the winds are coming in from the northwest at 25 knots, and I'm trying to figure out if I'm making a forecast for tomorrow, I'll want to multiply that by 24 hours. So if I take 25 knots, and let's make that 25 miles per hour is the average wind speed. I'm going to use knots and miles per hour interchangeably here. There is a subtle difference there, but 25 miles per hour, 24 hours. Let's see, that would be 10 hours would be 250, 20 hours. So it would be 600 miles. We would look 600 miles back to the northwest to see what type of temperatures are coming in. And again, that's because if the average wind speed is 25 miles per hour, by looking at the three stations here, and we're looking 24 hours into the future, that gives us 600 miles to look back upstream. If you look east to west across Iowa, that's about 300 miles. So from here to here is about 300, and from here to this point is about 300. So the air that's sitting up over central North Dakota today should move in by tomorrow. And I see the temperature here is 7 degrees Celsius. If I look between Davenport here and Omaha, the temperature would be 10 degrees Celsius in Des Moines currently, well, as of 12Z this morning, because we're about halfway between Omaha and Davenport. 12 in Omaha, 8 in Davenport, about halfway would be a 10 degrees Celsius. If the air 600 miles upstream is moving in, then I would forecast for an 850 millibar temperature of 7 degrees Celsius. So let's take a look at the 500 millibar level. And I see this 12Z map from this morning at 500 millibars. Again, this is about 3.3 miles up. It's minus 15 in Omaha, minus 14 degrees Celsius in Davenport. We're about halfway, so that would be about 14.5 degrees Celsius. Let's make the math easy. Let's call it 15 degrees Celsius. Now, notice at 500 millibars, the winds are out of the west. I have a westerly wind at Davenport, a westerly wind at Omaha, westerly wind up in Minneapolis. And so instead of coming out of the northwest, the winds will come out of the west. So if I look back, and again, let's pick a few stations here and get the average wind speed right around our area. 25 knots over in Davenport. See, this is why it's important to be able to interpret a station model. Homework number 1. 40 knots over in Omaha, so about 65 knots between the two. Divide that by 2 is 32.5 knots. Let's make the math easy. Call it about 30 knots and estimate it to be about 30 miles per hour. So we're forecasting for 24 hours into the future. So 30 miles per hour times 24 hours. Let's see, 30 times 12, 360. So that would be 720 miles back to the west is where the 500 millibar airflow is coming from. So if Iowa, again, keep in mind, average wind speed we're saying here is 30 knots times 24 hours would give us 720 miles back to the west. It's just like if you got into a car, went 30 miles per hour for 24 hours, you would travel 720 miles. So if Iowa is roughly 300 miles east to west, so from here to here would be about 300, here to here about 600, and another 120. So really the air temperature out here, it looks like in eastern, let's see, that would be eastern Wyoming. Get my western states right here. We see that the air temperature is about minus 17. I'm looking at this station up here in northeast Wyoming. So assuming that temperature of minus 17 is moving in, will be a little bit cooler than today at 500 millibars. So 17 degrees Celsius coming in on westerly winds, moving into Iowa tomorrow. So we're forecasting an 850 millibar temperature of minus 7, okay, minus the temperature at 500 we're predicting to be a minus 17, so a minus 7 minus a minus 17 gives us a positive, so there's a 10 degree temperature difference between 850 millibars and 500. In other words, the spread of temperature between 850 and 500 is 10 degrees Celsius. Again, I'm predicting a minus 7 degrees Celsius at 850 and then a minus 17 degrees Celsius moving in at 500. So the spread in temperature is only 10 degrees. That is well below the threshold of at least 25 degrees spread between 850 and 500. So if I'm predicting for stability or unstable air mass, we have to have at least a 25 degrees Celsius temperature change. I'm only seeing a 10. So for tomorrow, I would consider the air stable. In other words, it's not going to rise very much without any type of surface feature lifting it. So for question 13, again, if I go back here to the forecasting link, guess I should have left that up. So if I go back down here, factors I have to evaluate: sufficient moisture. When we looked at the 850 millibar map, it looked pretty dry. Frontal position, I didn't see any fronts in our area. And an unstable atmosphere. Well, the atmosphere will be stable because the temperature difference is only 10 degrees. To have an unstable atmosphere, to have moist air to rise, we need at least a 25 degree difference. So I'm not going to check the unstable atmosphere because of the 10 degree difference between the two levels. Well, I hope this helps. And for the part 2 of this lab, for the instability, I will give you some 850 millibar and some 500 millibar maps to analyze, and basically to do what I've shown you what to do on this particular video. Let me know if you have any questions, and have a good day.